Okay, this is the second part of Chapter 8, 6 in Geometry, Vectors. Unfortunately, I couldn't squeeze it into 15 minutes, so we're going to talk about resultant vectors now. Okay, so this was at the tail end of the last video, but the resultant vector, as we know, is the vector that represents the sum of two given vectors. So we can add them geometrically, or we can add the vectors the head-to-tail method, which is the parallelogram method. So we just kind of reviewed those. We said that you can combine the vectors using the head to tail, where we have an initial vector, initial point, terminal point, and then we put the second vector, initial point, at the terminal point of the first vector. And then we form a triangle, which is the resultant vector, which joins the initial point of the first vector to the terminal point of the second vector. So it combines the two. The second parallelogram method is when we use the same initial point for both the vectors. So we have vector u, vector v, and we create a parallelogram by adding a copy of those two vectors just opposite them, right? And when we do, the resultant vector is the diagonal of the parallelogram formed. So we can see that it is u plus v, vector u plus vector v. Okay, so let's try this. To add vectors, we can add their components. So if vector u is given here and vector v is given here, then vector u plus vector v, or the resultant vector, would be the sum of the two horizontal directions, right? And the sum of the two vertical. So let's look at this aviation application, and then you can try one for a kayak. So an airplane is flying at a constant speed of 400 miles an hour. So remember that speed can be written as the vector, right? At a bearing of north 70 degrees east. So taking north, we're going 70 degrees east from north, which gives us 20 degrees if we weren't using a compass bearing. Okay? So what are the plane's actual speed and direction if the wind is blowing at 60 miles an hour due north? Okay, so we've got the plane and the wind. So if we sketch these, that's what we have. All right. So now we can write the vector for the airplane in component form. The airplane's vector has a magnitude of 400 and makes an angle of 20 degrees with the x-axis, right? So we can find x and y, right, in a number of ways. Let's use our trigonometric ratio. The cosine of 20 degrees, cosine, remember, adjacent over hypotenuse, can help us find x, this horizontal distance. While the sine of 20 degrees could help us find y, opposite over hypotenuse, right? So that's what indeed they do, right? So the cosine of 20 degrees is x over 400, or 400 times the cosine of 20 degrees will give us x, which is approximately 376, a length of 376, or 375.9. Sine of 20 degrees equals the ratio y over 400, so y would equal 400 times the sine of 20 degrees, or 136.8. So we now have the airplane's vector, change in the x, and change in the y. Now, in order to find the resultant vector, we would want to combine this vector with the wind vector, right? So the vector for the wind in component form is there is no change in the x, right, when we have a vector that's going due north, but there is this change of 60 in the y, which again was the speed, 60 miles an hour, 60. So we can sketch the resultant vector and add the components. We don't even really need to sketch it, but we can add the components, right? So we would have 375.9, 136.8, the plane, add it to the 060 wind, and we have 375.9 in the x direction, and 196.8 is the resultant y direction. So in component form, there you have it. Isn't that cool? So we could imagine going 375.9, just as the plane did, but now in the vertical direction, we're going 196.8, right? And remember, the plane was going 136.8 in the vertical direction. And so the plane is now going with the wind steeper than that, isn't it? So 196.8. To find the magnitude and the direction, we would do what we were doing earlier. The magnitude of the resulting vector would be the distance formula for the x and the y change, the change in the x and the change in the y. We simply square them, right, and take the square root. So we have 424.3 miles per hour. The wind is kind of increasing the speed, isn't it, of the plane. And the angle measure formed would be the tangent again. Remember, we opposite over adjacent, or the inverse tangent of that ratio, which gives us 20 degrees, or a compass bearing of north 62 degrees east. Okay, so I would like you to try to answer this question. Suppose a kayaker paddles at 4 miles an hour at a bearing of north 20 degrees east. Okay, what are the kayak's actual speed and direction? I've got to give you the current, right? Just a second. Okay, so I'm going to let you know that the current is going 1 mile an hour due east, or another way to look at that, I'll give you the angle, that would be a 0 degree angle. With a bearing, you could say north 90 degrees east, right? Or a 0 degree. So go ahead and see if you can find the actual speed of the kayak, the direction of the kayak, and then come on back after pausing the video. Try that out, see if you can answer this question. Okay, so hopefully you've drawn it, and we have the current, and we have the kayaker. So the 20 degrees east of north, right, gives us a 70 degree angle for our triangle, right? And we know this 4 mile an hour for the kayaker. Okay, and then we have this 1 mile an hour current going due east. Okay, so again, we're looking for the actual speed, so we're looking for the resultant vector, aren't we? So we can identify the components of this vector. So sketched it, right? So we want to write the vector in component form for the kayaker, and so let's take a look at it again. So we would like to use this 70 degree, right? Opposite over hypotenuse would give us the y, right? So we need the inverse sign here, and adjacent over hypotenuse for the 70 degree angle would be the cosine, or the inverse cosine would give us x over 4. Okay, so hopefully you did that, and you found that the resultant x value is 1.4 and the y value of 3.8. So here's our component form of the kayaker's vector. We now need the component form of the current, right? And here's the current. All it's simply doing is going one place in a positive direction in the x direction, right? It's not moving at all in the y direction. So the component form would be 1, right? A change of 1 in the x direction and 0 in the y. So there you have it, 1, 0. The resultant vector then would be the sum of our two x's and the sum of our two y's, right? Components. And so when you sum these up, you get 2.4 and 3.8. So the resultant vector in component form is 2.4 and 3.8. Okay, so once you have the components of the resultant vector, we can imagine drawing that, right? 2.4, 3.8, and there we have a new component resultant vector, right? And so we would use that to find, we need to find that magnitude, that distance, which is like a hypotenuse, isn't it? And we need to find the direction, so the degree that's missing, okay? So to find the magnitude, we simply use our distance formula. Pretty easy, right? 4.5 miles an hour, okay? And so the current is given a little push, isn't it? And then we are looking for the angle measure, and so the angle measure would be, we have the inverse tangent, right? Because we have 3.8 over 2.4, the known, opposite over adjacent. So that ratio, the inverse tangent of that ratio gives us a 58 degree. And when it comes to the compass bearing, it would be north 32 degrees east, right? 32 plus 58 equals 90. Good. You're now ready to try the lesson quiz. So go ahead and pause, come back and check your answer. So in component form, vector ST, we have 13 and -6. Good. And we need this in component form, vector V, we have 9.7 and 7.1. The magnitude and direction, okay, magnitude again is the distance of that hypotenuse, right? The direction, you're going to have to go find the inverse tangent, and you found, I hope, 6.4 and 51 degrees. Find the sum of these vectors. And so we simply have 5 and 2. That's easy. It's already given to us in component form. You simply add, right? Then find the magnitude and the direction of the resultant vector. Okay, so we have 5, 2, magnitude, 25, 4, 29 square root of 29, right, about 5.4. And the direction, inverse tangent of 2 over 5, and you have 22 degrees. Good. And a boat is heading due east at a constant speed. There's an 8-mile-an-hour current moving north. What's the actual speed and direction? This is worth your time. Okay, I know this is tedious, but using this information, you broke down the components, a resultant vector, and then you needed to find the resultant vector's magnitude and the inverse tangent for the direction. So it puts it all together, and you have 35.9 miles an hour and north 77 degrees east, right? Very good, awesome job. Here's your assignment. Good luck, have fun, enjoy. I'm sure you will.